Hello everyone. My name is Yoshihisa.
Technical Director of Hedgehog Engine. 始める前にリマインダーです。
This is the reminder.
This speech is in Japanese. If you don't have a headset and would like to hear the simultaneous translation, please pick up a headset in the back. Please fill out the evaluation forms and turn them in. Please turn off all cell phones and pages. Okay? では、始めます。
Shall we begin? Please put the headset on. Are you ready? Hedgehog Engine is our company. Today, I'd like to talk about Sonic Unleashed, global illumination in Sonic Unleashed. This is our game engine to improve the quality of our graphics. I'd like to talk about that today. Global illumination is the most important element to support the quality of Sonic Unleashed. We have a lot of trials and errors, and we had a lot of difficulties in doing this, and it's not the necessarily a very positive story, but I'd like to share with this today. And if you learn something from me, I would be really happy about it. Okay, let's move on to the first slide. I'd like to talk about the chapter 1, the road to global illumination. How did we start this project? How did we introduce global illumination? That was 2005. At that time, gameplay and graphics have to have a higher quality, aiming at 2008. In order to start this project, we had a goal. We wanted to have a Pixar quality. We would like to improve our quality to the animation quality, even though that's the graphics. At that time when I talked about that, the artist didn't get it. They didn't think that we can do it, but don't worry about it and just do it. That's what I thought. Back in 2005, we could access to the high-end games platform such as PS3 and the 360. We took a look at a lot of graphics in order to make use of this high-end performance, but something is not right. For example, they use normal maps, HDR, shadow maps, cool shaders. They use these nice gadgets, but something is wrong. It doesn't look like 3D at all. That's what I thought. During the PS2, they are using the PS2 graphics with normal map. It looks a little bit richer, but it's not good enough. That's what I thought. Then, there must be some problem at the backside where objects are not lit by parallel or point lights. Because of that problem, it looks flat. Maybe because only the colors of different textures are used, everything looks so flat to me. We wanted to eliminate this flatness, and we wanted to make everything look more 3D-like. Okay, so what about pre-rendered CG? That's what I was interested in at the time. What are the differences between pre-rendered CGs and real-time CG? I was really interested in that point, so we collected thousands of CG images and observed. These are the examples I collected at the time. They're very beautiful. I showed these images to artists, and then I wanted them to understand what I would like to achieve here. By taking a look at pre-rendered CGs, in general, they have a good 3D image. By and large, they have a good three-dimensional presence. Dented area are depicted darker, just as they should be, and the lights are reflected. The light is reflected off the wall, and the other side is lit, as you can see here. This is another example. Various light is reflected off the surface and then lighting other objects. For example, you can see yellow light on the blue wall, as you can see here. Various lights are reflected. And I decided to take a look at the real world. I can show you several pictures. This is actual picture of our office. The light from the red wall is reflected and hit the white ceiling and the white wall, as you can see. It may be difficult to see here, but there is the light from the red wall is reflected. And this is another example. The light from the red box hit the side of the white mouse. And in between, there is a darker place. I see. As I thought, reflections are the key to high-quality visuals.
So let me go off track a little bit here. In 2005, the keyword for real-time CG back then were listed here, but I had some thoughts about this, so let me talk about that. The first keyword that we heard a lot was ambient occlusion. It just darkens a concave area with no consideration to light reflection, so perhaps it lacks expressiveness. Next is hemispheric lighting. It doesn't suit terrains. Even when applying it to character or objects, it requires many hemispheric lights to set up, so not so cost-effective considering the effort required by the artist. Now, vertex color, though it was the norm in PS2, color quality is dependent on the size of the polygon, so it lacks precision of expression. Certainly, Maya 3D Studio Mac Studio can be used in order to bake in the light reflection, and that would allow us to see something that's GI-like, but the shadows will still be undefined. So, we decided to give global illumination a try. We thought we needed to store the result of light reflections with higher resolution. And then if we do this, then we would be able to pre-calculate the reflections and bake them into the textures. Perhaps that might be a way to do it. In other words, we would use a light map. So up to this, I think anybody would come up with that. So then, how should we implement this? First of all, I needed to tell my colleagues what type of images I wanted to do, what I wanted to do, and we discussed how we were going to be able to do this. We spoke for about 30 minutes about what light is, and he said we do this, and then we do that, and we talked about various things, and he thought, okay, maybe this is doable. So let's give it a try. So my colleagues got very busy. And after 2 months of trial and error, ta-da! And here is the sample. So this is what we made in order for experiment back in 2005. It is a real-time image on PS3 or PS2 or Xbox 360. At this time, the processing speed was actually fairly slow. Here's another sample. And this is what it would look like. So the concave areas are really dark, as they should be. And you could see the light that passes through the leaf is a little green. So I thought, well, that was pretty good. So I noticed that the artists were very excited after they saw the demonstration as well. Great. So let's move with this. That's how I felt after looking at the results of the test. However, we had no idea that we were going to have a long and painful struggle in front of us. Chapter 2. Global Illumination Algorithm for Terrain. Now, first of all, let me talk about GI for terrain. Let me tell you about how we calculated this. Or how can we calculate this? Can we use ray tracing, radiosity, photon mapping? No, actually not. We didn't use any of those. In fact, we didn't know very much about those methods, actually. So we decided to create a very simple way of doing this ourselves. First of all, we started with a proof of concept. We created a light model. Think of light as a particle with energy that is transmitted in every direction. Light particles travel in a straight line after being emitted from a light source, and this is a ray. Once the light particle hits an object, the light particles is temporarily absorbed by the object. Depending on the material of the object, some of the particle's energy is absorbed by the material. And let's say the rest of the energy is split up and retransmitted as multiple light particles. So this is the rule that we decided upon. Well, I think this is pretty simple, isn't it? And we also assume that the speed of the light particle is infinite. There's no difference in arrival time of the particle based on the distance from the light source. So no matter what the difference, the light source will arrive at the same time. So based on this basic principle, let's break down lighting calculations to a simplistic level. We'll assume that one light source emits multiple light particles. And let's calculate the trajectory for each particle. When this hits something else, it'll spawn multiple particles from that collision point, and then we calculate the trajectories for each one of those new particles. And as they hit yet another object, we'll spawn more particles and keep repeating that process. Let's suppose one light source emits 100 light particles, and that one collision splits one particle into 100 particles. So when one particle emitted from a light source spawns 100 times 100, that's 10,000 particles when it collides with something. And of course, we assume that all these particles collide again, generating 100 more particles per collision. Then that's 100 times 10,000, and that's 1 million particles. But if we were to use this kind of calculation, a supercomputer would take 100 years to come up with a result. So perhaps this is not the right approach, we thought. So we decided we better start over again. We decided to limit the infinite number of calculations to a finite number. And so here we started Terrain GI calculation phase 1, creating a light network.
First, we create the texture, and then for each texel, we can treat each texel as a microfacet. This is called the GI texture. For each microfacet, shoot an arbitrary number of rays radially. Store the information for each microfacet that was first intersected by the ray. You don't need to worry about specularity at all at this moment. Do this ray calculation on all microfacets. When this is done, a ray network is created in space, as you can see here. Then, check the diffuse texture that overlaps the microfacet and determine the material's color. This is reflectivity of light. GI texture is usually coarse, and then you just need to check the overlapped place so that you can determine the color. Lots of texels from a diffuse texture will overlap a microfacet. Then create light source model. This light model might be you're familiar with this. First, we will decide the parallel light, and we can see we will hit the parallel light to the object. The blue part is an object. The light hits the object, and then the target doesn't have the light. And if it's shine, that means the light hit that part. The same thing happened. We use the same thing to point light. The vector direction is different. It goes to the point light. You can determine which part is dark and which part is light. And this is a skylight. It's a little bit different. There are so many microfacets, and actually there are a lot of rays which come from the one microfacet, and then you will remember the ratio. This is like ambient occlusion. As you can see, skylight, parallel light, point light are considered, and then you can pre-calculate this number so that at the phase 1, so that you can link this to the light network as we calculated before. At this point, we are not sure which color would be put on here. There is only network here. Then I'd like to talk about terrain GI calculation phase 2, lighting calculation. In the phase 2, we actually calculate the color. And I'd like to talk about light calculation. First, we create the entire value. The first one is 0. That means dark. It's dark. Number 1, first, we thinking about direct incoming light energy. This is the total sum of incoming light. And then we remember this number. Then indirect incoming energy. The total sum of emitted light energy visible on all microfacets from a calculation in the phase 1. Number 3, we will calculate total incoming light energy. This is the sum of number 1 and number 2. Number 4, we will calculate emitted light energy. First, there is the number total incoming light energy times reflection times adjustment coefficient. that is divided by number of rays from a microfacet. We will calculate these numbers from number 1 to number 4 per each microfacet. So sometimes we have to do 10,000 calculations. We use a double buffer to alternate calculation. And then we repeat these steps 1 through 5 as much as you want. And then you can come up with certain number. One iteration of steps 1 through 5 will result in darkness. This is a state where a surface is lit directly from a light source in space. Any location other than the area will be dark. 2 iterations is equivalent to all light in that space reflecting off surface. At this point, the microfacets that were dark on the first iteration is lit by reflected light. New light energy has been supplied to surfaces that are directly lit by the light source. 3 iterations is equivalent to all light in space reflecting twice. Given an adequate number of iterations, the amount of light energy supplied to the microfacets nears the amount of emitted energy. At this point, there is not much change anymore. Theoretically, the values should converge after an infinite number of iterations, but a reflection setting of 4 to 5 iterations is more than enough to achieve desired results. This is a core part. Then we need to do emitter coordinate correction. What is all this about? When shooting rays from a microfacet, it's normally done from the center of the microfacet. However, if the point of emission is located on the back side of the polygon, the microfacet is determined to be inside the object, resulting in black. This will result in a black band along the point of polygon intersection. To avoid this, we pre-calculate whether the center point of a microfacet exists on the back face of a polygon. If that is the case, the point of emission for the rays is offset to the backside. When a polygon was at the middle of if the polygon is half of the polygon is inside of the object, you can use this technology. Now I'd like to talk about color resolution correction. If we simply baked colors into a GI map, there is inadequate color gradation headroom in dark areas to generate good-looking gradients. To deal with this problem, we raise the color resolution of dark areas by calculating the root of the RGB value during the pre-computation process. We use the square of that value on the game hardware. By doing this, you can have a good color. Now I'd like to talk about terrain GI lighting results. This is actual game images, like this. As you can see, red rail reflects the light to the white wall, as you can see here. Like this, and like this. This is GI textures only. The ground is brown, so the lower part of roof looks brown, as you can see here, because the light from the ground hit the lower part of the roof, so it looks like brown. The ground itself is reflecting sky color, so it looks kind of like a light blue here. As you can, and then take a look at the tree. Because the light is reflected, it has stronger green, as you can see here. And this is a screen with no GI effect. It uses normal map, and also this uses basic shaders, but looks really flat, as you can see here. And then I add these two, and then we can get this. Like, see, can you see the difference between them? In the same way, this is a stage in China. This is only GI texture, and this is the shadow textures only. This scene doesn't have GI. Scene with GI, scene without GI. So you can see everything looks more 3D like. Then, as you can see, could you take a look at the yellow cloth? The light passes the cloth and hits the ground. I'd like to show actual demonstration. Okay. This, we saw this part in this picture. Okay, and then let me see. How do I do this? Okay, here. This is with the GI texture. Like this. It has color. And you can see the textile here. Can you see particles? This is the resolution. GI texture resolution here. Like this. And also, light goes through it, and then like this, and this, and this. Also like this. If you don't use anything, everything looks so boring. Boring. But if you put this, and then we have this, it looks much nicer. Looks nice. Okay. GI texture here. This one. This is actual sample. It's like the peeled orange and the skin of orange. You open up, and then we just open up the UV. And this is actual tree this is the GI texture for tree. This one, the texture for this tree, the GI texture for this tree is this. Also, the GI texture for a house, and the GI texture for the ground from the top, or from the above, from the sky. Okay, now I'd like to move on to the next topic. We give a little bit direction to artists. If an artist went ahead and prepared a background diffuse map as usual, they put so much energy in it, but I asked them not to do it anymore. You don't need to write any shadows at all. Just make it flat. Shadows, like this kind of making a diffuse texture, is only for one purpose, and then we don't ask them to use it to create shadows. Artists do not need to create any more textures so that they could increase the quality of their deliverables, but they could spend less time. However, our GI tracer generates indirect illumination calculations based on uneven polygonal surfaces, so we still had our artists manually draw in high detail shadows that would not have been generated by the resolution of the polygons alone. To facilitate the creation of the higher detail shadows, we created a tool called MI Tracer, Micro Illumination Tracer, that generated local GI calculations on the texture surface based on normal and height maps. By doing this, we support artists.
Now, Chapter 3, Global Illumination Algorithm for Characters and Objects. Since we achieved tremendous quality improvements in terrain and lighting realism, we still needed to deal with characters and objects, otherwise they look completely out of place and relative to the background. We needed to come up with a lighting solution that took into consideration reflected light 360 degrees around the character and moving around in 3D space. So then, what is often used is hemisphere lighting, but we thought that probably doesn't cut it in terms of render quality. It also is quite a task for the artists, so we decided not to take that route. And instead, we decided to partition space into blocks using BSP, and then set lighting information on the blocks' vertices to use as a light field to light characters and objects. This is sort of the image of what a light field would look like. First of all, the space is automatically subdivided into big and small box-shaped cells around, according to the terrain shape in an adaptive manner by BSP. A small cell is about 2 or 3 meters in size. Each cell's vertices has color GI information data that is automatically assigned by an offline tool, and the XYZ axes in GI global space provides 6 directions, light color data from 6 directions. And basically, this is pretty similar to what is called irradiance volume. Then, how did we use the light field? The cell where the base coordination, usually the center, is located on a character or object is sampled. Then, based on that, we interpolate the incoming light data for each vertex in a cell based on the object's coordination. That's the light blue line. There is a minimum of 8 sets of incoming light data from a cell. And based on this, the color information is calculated. That's the red arrow there. That's number 4. Calculate the color information of the incoming light coming from the normal direction. And then we use this color information of the incoming light instead of ambient light. This method enables detailed lighting and correctly represents light information that is reflected off of a terrain near characters and objects. Here's a sample. So you see in the center, you see the character Sonic. And the light field information is already in this, you could see. Now, here, this is where there's no light field. Because nothing is done, you can tell that the character sort of seems out of place and flat. When we add the light field information, this is what we get. On the left side, you have the magenta color. On the right side, you have a yellowish wall. You can see how here that is included as the light field information. The left side is a little bit magenta, the right side is a little bit yellow. And because of this, Sonic ends up looking natural in the space there. Here's another sample. This is Emmy. Because of the light field, the color looks natural. If you take the light field off, the character looks completely out of place. Let me show you a demonstration again.
Ready? Go! よし。ちょっと移動します。
So we'll move around a little. So this might be a really good spot to show you. So here, there are a lot of different colors in space, as you can tell. This shows the light field information that's used. The right side, we have green trees. So the right side of Sonic looks a little bit green. Around here, the wall is a little bit yellow, so you can tell that the right side of Sonic turned a little bit yellow. Now let's get close to the magenta color. The upper left part of Sonic turned a little bit magenta color. Then we have a red wall. You see how it's red on Sonic? So by doing light field that I explained earlier, we're able to show that type of a refractive color on the character. Now, when we don't apply light field, can you tell? You could tell that it really just looks wrong there. But when we add light field, this is what it looks like. So it blends into the scenery. No light field versus light field. You can tell the difference, can't you? See? So let's move a little bit more through this space. Whoops, I think I went too far. Now here, we have this green garden-like arcade. When Sonic goes underneath this, he gets a green hue cast on him. Here he's all white. You see how he turns green a little bit? And then when he goes outside, he turns white. Like this. Okay, I'll go back to the presentation. Now, we took things one step further to implement natural rim light derived from the entire environment to provide a more natural look for character shading. We call this light field rim lighting. Sonic and the villagers will have something almost like backlighting. And we want sort of more of a halo effect around the outside of the characters. So in addition to the normal light processing, we're using reflective vectors in order to bleed the silhouette of the character models, like the Sonic and Villages. In addition to normal light field process, the reflection vertex of the eye-ray vector is also used to calculate secondary light field. By blending the color information derived by that process, we can achieve a halo-like effect based on the subsurface scattering. This is not an explicit placement of a light source. It's effectively a rim light effect that is created for the natural light source that exists in that scene. Now, where was I? Where was the space? Whoops. Well, won't worry about that. No, where was it? Here it is. Whoops, I went a little too far. I'm trying to find a space where it's really obvious, so please be patient with me. Uh-oh, I'm sorry about that. It seems like there's a problem with the debugging tool, so I'll reboot it. I think this probably is a good spot for that. Okay, now here, let me show you where you can really notice the rim lighting. Maybe it's around here. It's a little dark. I don't know whether it really projects very well. Can you tell that? Can you see it? So the room inside is a little orange. And so you should be able to see a little bit of a orangish bleeding out around the rim of Sonic. Of course, if he moves into the light, it turns all white. And all of that information is provided from the light field. So because we're running out of time, I'm going to move forward. Now, the light field data size, I'm not going to go into details, but it's around 3 megs. In the bigger stage is around 3 megs in file size. Now, Chapter 4, Distributed Computing. Now, in Chapter 2 and 3, I talked about our GI maps and light field methods and global illumination as well. But just having that doesn't mean that we were able to achieve what we wanted. In fact, that portion wasn't the most difficult portion. Now here's the test terrain. This is 500 meters by 500 meters. And when we actually calculated this, on one PC it took 2 days. There were approximately 100 megabytes of GI texture data. Before we started doing GI, we knew this would be the case. But it just takes so much time to compute this because the data generated is huge. We actually already knew that would be the case. In addition, Sonic runs around the space at a speed of about 100 to 150 meters per second. He's actually faster than Formula 1. So how many kilometers are the game levels going to be in size? How much computing time will we need? How much data is it going to be? It depends on the level design, but the stage size it goes from 5 to 20 kilometers. GI's texture sizes goes from several hundred megs to 1 gig, which means computation time is going to be several months. Uh-oh, this isn't going to work. But I thought, oh well, maybe if we just try harder, it'll work. So if it's going to take a lot of time computing, then perhaps we should just distribute the computing. So we decided to try a distributed processing system. So you can see on the picture, on the bottom left, you see the artist PC. That is connected to the management PC. And then it says someone's PC. Those are other developers. So these are all connected like this. And then, so we provide them these type of calculation resources. GI texture and light field are very heavy calculations, but PVS and other really expensive calculations were done with the same system as well. So as we looked at this, as doing more of a distributed process system, we were able to cut down this amount of time that would take to 10, or by 1/10. So we thought, okay, if we set it up like that, we could do it in 1 or 2 evenings, but that wasn't actually the case.
Of course, in the phase 1, creating the light network approach is good for or suited for the distributed computing. So we could reduce the computing hours dramatically. That was really, really good. However, in the phase 2, we need to use a diffuse map or GI map, or these things took gigabytes. This needs a lot of memories. In the phase 2, we have the calculation. Usually take 100 gigabyte for the one level. We need to deal with these data simultaneously in the phase 2. Then we have a problem. With the 32-bit PC, we couldn't put the memory texture. There is always swap between memory and hard disk. In the light network, in order to access to hard disk, it takes forever. It was a bottleneck. So we decided to use 64-bit PC, and then we increased the memory to 16 gigabyte. Also, we used the fast hard drive with the red zero striping configuration, so that the speed, we have a much faster speed. Also, we compress the light network data from 100 gigabyte to 70 gigabyte. By doing this, we reduce the access to the hard drive so that we could have faster speed, so that we could finish the calculation within hours. That was really good. Because of these efforts, we could reduce the calculation to 1 or 2 nights instead of days. I thought we could solve the problem, but not yet. We started using high specification PCs, and then they started moving, like hundreds of PCs started operating simultaneously. As a result, darkness. Because we had a lot of load on the power, we have a short circuit and we lost the power in the office. Okay? Then we stopped using microwave ovens. That's the number one thing I did. You can't make coffee anymore. You can't use a coffee maker. But it doesn't do any good. That's not helping. So we needed to add more power to the office. That was a huge construction. We created a huge mess here. Finally, we could calculate massive numbers. Okay, now let's move on to chapter 4. In chapter 3, we created more capacity to finish the computation. But now we have to deal with other things. We had to deal with the problem with the new hardware. For example, it's easy to create a small scale of games or small action game, but we are making a Sonic the Hedgehog game. We need to create a bigger scale because a character runs very fast. So 1.5 to 20 kilometer level comprised of model, data, GI map, textures. And then it can scale from several hundred megabyte to around 1 gigabyte in size, so that we don't have this memory capacity, so we couldn't deal with it. So we needed to deal with this problem. First, we started doing independent MIP level loading. All GI maps were split up as MIP level 1, 0, 1, and 2, and set up to be loaded independently. Sometimes memory can't catch up with it. Then we use the GI map MIP level 2 or 1. red is 0, green is 1, blue is 2. Now let's talk about GI Atlas. With Xbox 360, we were supposed to use only 5 megabyte, but actually we consumed 15 megabyte of RAM because of the memory alignment. 8 times 8 equals 16, and then it uses 12 kilobyte. With the mid-level file partitioning, we have so many files, and then we waste a lot of memory space. In order to deal with it, we collect small files and then consolidate it to reduce memory consumption. Also, we reduce the wasteful seek time to the disk. Now let's talk about file packing. We had a huge number of files, so we'd like to consolidate them as well. We'd virtually consolidate them. And I'd like to talk about the manual tuning feature. This feature was implemented to enable manual tuning of streaming and culling. This was implemented via placement of collision objects with a level that would set a flag if a player passed through the area. Sometimes we have errors of PVS judgment, and then we had to deal with it. Audio playback. We don't have a lot of memory space here, so that we needed to make use of it. In order to fully utilize data coming off the DVD and BD for background data streaming, all the music and the sound effects data was read into memory. We used up 40 meg, but we have a big return from it, so we decided to do this. Now I'd like to show you the dynamic demo a little bit. He was sleeping, wasn't he? Red is MIP level 0, green is MIP level 1, blue is 2. Sonic is running, then more blue or more green, as you can see here. It stopped, then it close to red. Like this, it's being loaded. So this is the demonstration. I'd like to talk about the DVD. So stage a number. We have several stage numbers. In 360, we don't have enough memory.
Since this is an action game, and because of the game design, we can only use one DVD, but we couldn't have put everything in DVD. We decided to take, rather than putting the high resolution MIP in the DVD, we decided to happen to include the information in the DVD lay offline. And unfortunately, we don't feel very happy about this, but even if it was low resolution MIP, it actually didn't really lower the quality. Actually, this really brought home the value of the power of GI. So now I have a request to Microsoft. For the next 360 hardware, please don't use DVD. It doesn't hold enough data. And incidentally, I also have a request to Sony as well. There's going to be a day when Blu-ray isn't going to be enough. There should be a larger capacity, higher speed media as well, and we would like a lot more RAM. Chapter 6, Conclusion and the Future. As you could see, we devised various methods to realize graphics with global illumination visual aesthetics in real time. But what we concluded was that it was really painful. It was just incredibly painful, but it was very effective. It wasn't just because of the higher image quality. Oops, wrong direction. It really made our artists really excited. Their eyes started shining. And they didn't really care about working nights or weekends. They were willing to dedicate themselves to the work. So the artists really, really worked hard. But thanks to that, I think really the quality of the image really increased quite a bit. So it was actually a positive spiral. Well, certainly it was very difficult, but we were extremely satisfied with the result. So what issues are there in the future? Now, one issue would be light fields for large objects, dynamic global illumination, and move from view-independent GI to view-dependent GI, as well as Wii support. Now, as far as light fields for large objects, you can tell by looking at the drawings on the right. As long as the character can fit into the box, it's fine, but when it's bigger, it's a problem. For example, you might have a big character, boss character. We might have to do the lighting and separate them from the upper body to the lower body. We weren't able to get that far last time, so we would like to do that in the future. Now, as far as dynamic global illumination is concerned, I think this is probably the most important point. This system that we had this time, the assumption was that the point light and the light source were not going to move. They were static, so it was static information. However, we would also like to use GI even for moving light source as well. This is actually pretty tough with the current hardware, but if we set limitations, we might be able to use the method that we devised, even with the limitation of the hardware. And then we also have the view-dependent and view-independent GI issue. Our system looks the same no matter where the viewpoint is from. But when when we have objects that actually have sheen, then we have to think about the specular reflection. We wanted to have also GI information that takes into account the specular information as well. Well, the character itself is already dynamic, so that is actually not where this would be applied. Now we support. There are two issues with GI support with Wii. First, we can process the Wii SKU's level data through the Hedgehog Engine's GI generator. And then second, we can implement GI maps and light fields on the Wii version of the game, just like on the high-end console. We're currently looking into both of these, but let me show you what happens when we take the former approach. We ran the Wii game data through the Hedgehog engine. So this is the Wii version. It's from Sonic and the Black Knight. So with the Hedgehog engine, this is what will result. You see the difference? The polygon is the same as for Wii. It's exactly the same polygon count. We just added the GI. And this is on PC. But with 360, it's the same as well. So if you compare them side by side, this is what it looks like. So you could see, even with Wii, just adding GI actually will give a certain amount of impact. So this is Wii. This is with HD or the next gen. When you compare it, you can tell that the next gen has much more of a 3D feel. We have other screenshots like this, you see? After, before. So the polygon data is the same, but using Hedgehog engine and the tracer, you could see what a difference it will create. This was the data from the Wii version. And then this is what it looks like. So I need to add something it's not to say that Black Knight is being developed or being ported onto the next gen. Basically, we only use that particular title to experiment with the images. Now it's QA, but actually we only have 1 minute left. Any questions? Well, if you have a question, you can come up to me later. After this, and we can talk about it. So that's it. Thank you very much for coming today.